Okay, let's get started.
All right.
So
I think,
yeah,
if you want to.
welcome everyone to Andrin's defense or presentation. And so my name is Robert Feldman. I, essentially supervised Andrin, and Andrin did his bachelor at the University of Zurich in the computer science program, did a minor in computational science. That's how he's probably got sucked into the whole business. And then decided to do a master's in computational science. And, that is what he's going to talk about today. And he has, as you perhaps know, he has a lot of interest in machine learning and AI and how you can apply this essentially to natural science. So, Andrin, I hand over to you.
All right. Yeah, thank you. And yeah, welcome everyone also from my side to the presentation. My master thesis, which is titled Predicting Dark Matter Initial Conditions. And yeah, I guess the rest should be more or less obvious. I mean, the others are also, so Douglas is over there and Marvel is over here. So we're all ready. All right. So we'll start off with the problem statement. And on the left side, we have the initial conditions of a galaxy or a cosmological simulation. So that's like a few billion years ago. And we denote the state which we have selected as like a redshift of 49. So it is kind of a notion of time for people who don't know that. And for the initial states of the universe, we only know like some characteristics, and we can do specific realizations or like random realizations with those specific characteristics. And we can then perform a simulation and end up with a final state, which can be like the time of now, so which is kind of equivalent with what is observed in the universe right now. And this one we denote with the redshift set equal to 0. And yeah, like the main question of this thesis is that can we go back in time, or like can we to some extent predict those initial conditions given a final state? And that can be very helpful if we want to say, yeah, we can do an approximation of the initial conditions and then do a very accurate simulation on this approximation, which is then going to help us understand the final state or like the observed state, which you can see of the universe right now. We are talking here about dark matter simulations. So dark matter is most of all matter in the universe. So you can kind of say it's more important than real matter, or real matter doesn't matter. And dark matter is also easier to simulate because it only interacts over gravity. So you need to have account for less effects than if you do also do the real matter. And they're usually, or like in modern simulations or also simulations we have used, they're discretized as particles in a n-body simulation. So you have like a particle, and each particle has a notion of mass, velocity, and position. And we have created quite a lot of simulation data. So we did 2 data sets, a small data set and a large data set. The small data set has 100 time series, and the large data set has 300 time series. The small data set is 128 cubed, and the big one is 256 cubed, both in like the actual how the grade of the density field and also the number of particles we have. And we generated that using PKD-Graph3, which is mainly developed by Douglas over here. And the sizes, the physical box sizes of the simulations are 30 and 60 megaparsec. So the small one is 30 and the big one is 60 megaparsec. And here you can see like a 2D slice out of this 3D simulation box. And this is kind of over time, so that would be right now. And here you can kind of see the cosmic web. And here are the initial conditions. And then what we also have is the power spectrum, which is the thing I talked about earlier, which we know of the earlier universe. So we can kind of know what the power spectrum of the initial states or the early universe are. So here you can see the C with 49. That's kind of the information we know about the early universe. And this power spectrum gives us a notion of correlation over the scale of structures. So if we have a high value here, that means that the smaller structure, there's a lot of small structures. And if we have a high value here, that means a lot of large structures. And this tendency always kind of indicates that we have more small structures than large structures. So it's kind of dropping off towards the larger structures. And then one of the questions we could ask ourselves is, why don't we just simulate backwards? So if we can do forward simulation, why don't we just go backward and find the initial states like that? And it's a very valid question. But there's two main reasons why that doesn't work that well. First of all, the observation we have from right now, we don't see, it's not super well defined. You can see the 3D positions of the mass, and we can also see parts of the velocity vector, but not the entire velocity vector. So we can kind of figure out how fast an object is moving away or towards us, but we don't know like the angular velocity of an object. So that's why we cannot really well define a inverse simulation. And another reason is that it's, even if we would know everything perfectly, we can't do the inverse simulation perfectly due to numerical instability, and also because we can never really know the exact reverse velocity vectors, because we're always, if we're at this point, we calculate the acceleration from this perspective, even though we would need this vector. So these two vectors are never going to align perfectly. Then another thing which was actually very interestingly talked about in the talk from Oliver last week, so that's differentiable simulations, which is another way we can kind of solve that. So if we use automatic differentiation, we can implement a differentiable simulator and optimize for the correct initial conditions. So in here, you have like this equation, and you have the individual forward simulation steps. So we have like first step P1, P2 until Pn-1. And you start off with the initial conditions until you reach, when you reach like the outermost bracket, you have the final condition, and you compare it to the true final state, or the final state we observed, and you compute the loss out of this. And because it is differentiable, we can compute the gradient of this loss and kind of backpropagate this loss to the initial conditions and gradually increase the goodness of this initial condition. And naturally, you would start with like a random initial guess and gradually go to a direction where this is a good initial condition. Now, there's a few reasons why this is also very challenging. So implementing differentiable simulations is very challenging, and even the best AD frameworks still have a lot of errors, and it's still sometimes you need to use like float 64 byte because otherwise it will like give you nans, and there's always some tricky stuff with AD frameworks, especially when you have such complex simulations. Then the next thing is you always have like exploding and vanishing gradients when you try to backpropagate your gradients through such recursive systems, because here you kind of have this recursion of the simulation steps, and we want to get the gradient back through all of these steps, and that can be very tricky, and you get a very bad gradient in the end. And also a final thing is that the memory requirements grow with the number of simulation iterations, because in backpropagation, we need to store all the primal evaluations. That means we need to also store, when we unroll this over time, we need to store all the intermediate values as well. And that can be a problem, especially if we simulate or run this stuff on the GPU, where GPU memory can be constrained. There's some ways to solve that, but we'll not get into that. So our approach to this is just to predict it. So it sounds almost a bit silly. So we'll just throw a neural network at it. So we are given the final state, and we have a neural network, and we just try to find the initial conditions based on this final state. And we have opted for a specific neural network architecture, which is called the Fourier neural network. And I'm first going to explain you a Fourier neural network layer, and then I'm going to explain the whole architecture. So here on the very left side, you can see the real space density field. In this case, this is two-dimensional, but you can imagine that it's always going to be three-dimensional in the actual thing. And it's also real value. So that means if we do the Fourier transform, we end up with like half of the space here. And this one is also the shifted Fourier transform. So that means the larger modes are here in the center, And then the next thing we do is we kind of select the k largest modes, and we have this complex weight matrix, and we perform a complex matrix multiplication with this subselection of the k highest modes. We pad this with zeros and then inverse Fourier transform this again to get into real space. So that means our weight matrix is actually being applied in complex space. And this brings quite some advantages. So here we also have a skip connections that is kind of able to pass these like the Fourier space. And then we chain these Fourier neural network layers into this whole Fourier neural network or Fourier neural operator, how they call it. And usually you have like 3 or 4 of these layers. And the specific adaptation we have made in the master thesis is that the number of modes are increasing with each layer. So the first layer has less modes, and then we gradually increase the number of modes. And this is also partially because what we also will see later in our case, it is just easier and more possible to predict larger structures. So that means if we allocate more compute towards larger structures, it just makes more sense in our case. And one of the reasons why the FNO, I think, is a very good choice for this case is FNOs are inherently periodic, and our simulation boxes are also periodic, so we don't need to care about setting periodic boundary conditions, etc. Then the reason number 2 is that FNOs can handle very large dependencies over the entire domain, which is something if you use other like convolutional based neural networks, you always have to make sure that you kind of do a latent space, which is like compressed and then decompressed again to make sure that information can pass from one corner of the domain to the other corner of the domain. And this is not the case here since we're operating in pure space. Then, yeah, like the reason number 3, which is also going in the point from before, in other networks, in order to handle those dependencies, we need to compress the data into a latent space. And I think, especially with this data, this can be really tricky. Now we're getting a bit into the hyperparameters. So I did like some tests of the hyperparameters. So here you can see neural networks. We can see it that we're each trained with different parameters. And here it's the number of channels. So what we have seen before, we're doing that for 3D boxes, but we're also doing it in a latent space. So before we apply our neural networks, we promote our tensors or our 3D boxes into a latent space, which in our case is the latent space of 32. So we end up with boxes that are like 128, 128, 128 by 32, which are actually pretty huge. And this here is like the study of how many of these latent space channels we use. So we can kind of see that the more we increase the number of channels, the better like the performance gets. And here it's also interesting because we don't compare against the number of epochs, but we compare against the number of compute seconds, which I think is way more interesting than the number of epochs, because in the end, what we want is a network that performs best in the shortest amount of time. And you can see that even though the network size increases a lot, so here you can see the number of parameters, it still makes sense to use very large networks. You can still get a faster convergence with larger networks than if you use smaller networks. Now, because we have such like big tensors and these matrices, like the weight matrices also become super big, we have models which are up to like 60 million parameters, which is pretty big actually. But I think it's still reasonable because the data size is 5 billion on the large data sets, or 50 billion if you also include time. So that would be 50 billion floats, not like big bytes or anything or gigabytes. Then the next graph is also pretty interesting. So for this graph, we have trained, this is like 30 neural networks that were all trained for specific time regions of this data set. So you can kind of see on the right corner of your bar would indicate where the training or what is the initial state or what is the input of the neural network, and then the left corner is the output of the neural network. And then this axis kind of represents time. So here we're going towards now, and this is like the initial state of the simulation. And you can see that there's 2 correlations. So first of all, you can see that the longer this time frame becomes, the higher the relative squared error becomes. And also, the further or the closer we are to now, the easier it gets to making those predictions. Now, next of all, we are getting a bit into like structures. So it's certain, like I've already touched this before. So predicting larger structures easier than predicting smaller structures. And we can see this here. So this is like a prediction on the small data set. And this is a normal mean squared error here on this column. And here we can see the power spectrum of this prediction. And the blue line would indicate the real power spectrum of the ground truth in that sense. And you can see that this prediction will kind of fall off at some point, which kind of indicates that at this point, the neural network doesn't have anything to predict anymore. And this is also reflected here in the correlation, where you can kind of see the correlation dropping off at the same point, which also indicates that these corrections are not getting less and less accurate. But it's kind of interesting because it means that the neural network will kind of only predict things that it also can predict. So it will not kind of try to predict fantasy stuff because these two plots here align with each other. But interesting thing we can do is we can kind of force our neural network to predict stuff it cannot accurately predict. So we can, in our case, we programmed a differentiable power spectrum and we included that as a loss. And then we can force our neural network to not only predict the mean squared error or decrease the mean squared error, but also decrease the difference between the simulation or the truth, the ground truth power spectrum and the predicted power spectrum. And you can see here that this would be the orange line where we included this power loss, and you can see that the power spectrum aligns way longer until it falls off. But if you look at the cross correlation plot, you can see that the correlation kind of still drops off at a similar or even at the earlier stage. So which is indicating that this neural network can predict smaller structures, but these smaller structures are more like fantasy structures. So it's more like a generative thing, less than like actually being rooted into data, which you can also kind of observe visually here. So here you can see it's way more noisy and fine-grained with the power spectrum loss, and here it's way more smooth in that sense.
Andre, good question. So what is the cross correlation here currently before? Between which one, please?
This is between the simulation or like the ground truth and the prediction. Yeah. So the next thing we have tried is, because like the neural network architecture we are using is the pure neural operator, is a thing that people use in SciML, so mostly in like surrogate space. So what those people are trying to do is kind of to replace numerical solvers with neural networks. And what they usually do there is you don't just apply this once and predict the entire time span, but you actually apply this neural network repeatedly. So we can kind of borrow the same idea here and see if we get better results. So in that case, we use 2 neural networks or even more. It could be any number of neural networks. But the big difference between the approach that is done in regular surrogate training and our approach is that we use unique parameters for each neural network. So instead of using the same parameters and the same neural network for each time step, we use different parameters. And we have tried in the beginning a lot with using the same parameters, but it's just very hard to learn all the dynamics across the entire time span, because apparently the dynamics are just so different in the different time regions of our data set. So it makes a lot more sense to use unique parameterizations. I think there could be probably a way to encode something like a time embedding and make sure that this also works with the same neural network, and would be probably a very good way to kind of continue this project. But I tried it, but I was not successful, or we were not successful. So here we're getting a bit into like the training schemes we have used. So there's 3 training schemes we have used, and this is the stepwise training I'm explaining here, which is like the most simple one. So let's now for a moment just forget about redshifts and time, and if we're going back or forward in time, whatever. We're just saying we're at T0 and we want to go to T3. So we want to predict T3 with the neural network. And like the stepwise training is each step or each neural network is starting with the ground truth and then making a prediction. Then the next neural network is again starting with the ground truth, making a prediction, and so on. and then we evaluate the loss based on the ground truth and our prediction, and then we update the parameters of each neural network. And this is very like a powerful training method because it has very fast convergence, because the gradients are super accurate, because we don't have that much of exploding and vanishing gradients problem, because the gradients don't need to be propagated over so many such large neural networks. But the disadvantage of this is that this will not force the neural networks to kind of learn to deal with errors from the previous neural networks. Because in the end, what we want to do is we want to go from T0 to P3 directly. So that means if each of these networks do kind of errors, the next or sequential network cannot really deal with that. So the next thing we do is a sequential training. And in that sense, we don't feed in the ground truth anymore, but instead, the neural network will always kind of try to predict based on the will always try to predict based on the input from the previous neural network. But then still we compute the loss for each step and update the parameters for each neural network. Then the final thing we're going to do is the mixed mode training. And here we really kind of, this is really indicative, because in the end, we only care about P3. We only care about the loss prediction. And you can see in the previous thing, we also computed the loss on the intermediate steps. But for the final thing, we don't care about the loss of the intermediate steps. So we only care about the loss of the final step. That means we don't compute these losses anymore, but still backpropagate through the entire chain and update the parameters of each of the models. And in our final or like best model that we achieved, we did 20 epochs of stepwise training, 10 epochs of sequential, and finally 10 epochs of mixed mode training. And we got kind of I didn't do like a very exhaustive hyperparameter set of these training schedules, but it worked better than most other things I tried. So this is like the best model we have achieved. So in that case, these are 3 neural networks. That means one neural network goes from here to here, the next one goes from here to here, and the next one goes from here to there. And these are all individually parametrized. And you can see that here what we are really looking at is the yellow line. I think you can see it. So here's like the non-dashed, like the solid yellow line is the prediction, the power spectrum of the prediction. And then the dashed line is the simulation. And you can see that this is kind of aligning kind of well over K1, which like judging from the talk we had last week, I think is a decent value. Because Oliver from the talk last week said that in using differentiable simulations, they also expect to get something over K1 or like up to K2. And what we also added here is kind of skip connections between the neural networks. So that means these neural networks, they can also they can not only write a density field, but they can also write to a latent space. So that means in this latent space, they're able to kind of pass on information to the next neural network. So we have not really looked at this latent space, what exactly is stored there. Usually also pretty hard to understand, but it's kind of a way to communicate between those steps. Then another thing, I want to get a bit into the performance, because we spent quite some time like optimizing the performance of this entire training pipeline. So we have used checks primarily, which is like checks is responsible for all the automatic differentiation and all the the vectorization of the operations. It's based on XLA, which is like a library which has like parallelized kernels and also CUDA kernels for all of the operations. Then the data loading we did with NVIDIA DALL-E, which is super performant and can do parallelized and GPU accelerated pre-processing of data. And because we have quite large data sets, I think this helps a lot. So for example, the NVIDIA DALL-E would, if we want to like downscale our box, this would kind of downscale our box using a bilinear interpolation, which is super fast. Then finally, we used Equinox to implement our neural networks, which is kind of a wrapper around checks. Doesn't really impact your performance that much which one you use, but it's still a good library, I think. And then you can see that these are kind of the times we achieved here. And the training of the best model I've showed you before could have been or was done on a 100 GPU in something like 20 minutes, which is pretty fast. And this is training, right? So inferences can be done in 10 seconds or even less. And I think this is one of the really cool aspects of this approach, is that it's just incredibly much faster than doing the same thing with a differentiable simulation. Because when we do a differentiable simulation, for each time we want to do a realization of the initial conditions, we have to perform an optimization. And those optimizations, from what I've seen from PMWV, which is one approach, and also from Oliver, they will always use like thousands of iteration or optimization steps. And each of these optimization steps will have to go once through an entire simulation and then another time for backpropagation. So potentially it can be hundreds of thousand times faster to get an IC than like a differentiable simulation and gradient-based optimization. Then as a final note, I also want to highlight that some of the code we put it in a Python library, which you can kind of install now with pip install Cosmex. And there's mainly what we have seen here is the power spectrum and the differentiable power spectrum, which we kind of also used in the thesis, but there were some other experiments that you could do. For example, what you can do is you can generate an initial condition which has a specific power spectrum, but it also follows like some specific density distribution. So in that case, you kind of imprint the name of the library into the density distribution. Or another interesting thing you can do here is, because we also have a differentiable initial condition generator, you can also optimize for a white noise that will then generate a specific realization which has also kind of a specific name imprinted into it. So you can do all sorts of cool things. And there's also a differentiable mass assignment, so cloud in a cell mass assignment scheme, where given a density distribution, you can sample particles on the density distribution. And finally, it's pretty fast, so it's way faster than the PowerBox, even only on the CPU. And this is especially true if you do multiple iterations. So if you have an optimization scheme and you want to use a power spectrum in the optimization scheme, this approach is going to be way, way faster than other approaches. This is like because Chex uses just-in-time compilation, and just-in-time compilation will compile your Python code on the first execution. So that means the first execution is named the warm-up execution, which will take longer. And then as soon as the code is compiled, then everything is going to be faster. So we're already getting to the conclusion. So I think predicting initial conditions with neural networks is definitely a promising area of research. And some of the things we have seen are also indicative that surrogates for inverse or non-inverse body simulations are also, I think, a very promising area of research where I've not seen a lot around, but I think it's definitely doable. And I think those initial conditions could be either used directly as initial conditions for simulations, and then we can still add back the small scale structures using traditional methods. Or we can also use it for initial guesses for differential optimization. So even though we could, for some reason, we think these are not good enough, and we want to have better initial guesses or initial conditions, we could still prime an optimization scheme with those and probably cut the number of optimization iterations by quite a large amount. Yes, and that was pretty much it for my presentation.